Okay, so this is the last talk, last but not least, is Katherine Seery. We'll be talking about the question, what are some of the conditions for star and planet formation?
Okay. Thank you for that introduction, Dr. Feiger. Like you said, I will be looking at a spectrum, a millimeter wave spectrum, of a circumsolar disk around a young star called the calcium 15. So a little bit about what I'm going to go over today. Basically, my question is, what are some conditions for star and planetary formation? I'll go into what some of the literature says is the current star and planetary formation theory. Some possible steps towards answering this. I'll go through the observations of the calcium 15, the reduction that was done, the analysis, and then I'll discuss and talk about future works. So, basically, the literature says there's kind of four basic steps. Basically, you start out with a giant gas cloud, and it starts collapsing because it's cooling, and a protostar forms in the center. Then you have the young protostar, and the other collapsing gas turns into a disk because it's cooling and conservation of linear momentum. And it starts out going into what's called a settled disk with clumping. It's still accreting onto the star. And then that dust starts clumping into little planetesimals. And then you get what's called a debris disk, and those clumps turn into kind of what we think of the modern day solar system. So in order to answer this, we would basically need to observe objects in each stage of this evolution. So how can we start to answer this? You can take a spectrum of each stage in the evolution, and then you can look at those emission lines and figure out what elements and molecules are contained within that gas. And then you can use those emission lines to figure out line intensities, which help you estimate temperatures, velocities, column densities, and mass, and all sorts of other things. So that's a very big question. So I focused on this calcium 15 star. A little bit about it. It's a pre-main sequence with a circumsolar disk. You can see it right here. There was a paper published in 2011 about it being the first ever image showing possible protoplanets being formed, but that's widely debated, so I'm not going to go into that. But the age is about 2.5 million years, and it's about a solar mass star, which may be interesting so we can see what our past looked like, maybe. So a little bit about the observations. There were 9 observations in March of 2012 on the IRAM 30-meter telescope. The fast Fourier transform spectrometers were used, and we got a total coverage of 208 to about 270 gigahertz. The spectrometers were put into 200 kilohertz spectral range mode, and you can kind of see the way the spectrometers are set up. You have to get 8 gigahertz set, and then another 8 gigahertz. So there are 16 for each observation. So it kind of looks like this. There's 8 gigahertz, 8 gigahertz, and these are all the observations. So a little bit about the data reduction that was done. Most of it was done in class software, which is available in the Build This package from IRAM. So there was basically a polynomial was fit to the spectral baselines, or the continuum, that avoided the bright spectral emission lines. And this polynomial that matched the spectral resolution was then subtracted to yield basically a flat continuum. And then the noise was looked at, and it was approximately uniform at about 7 millikelvin on the antenna temperature scale. And then within class, you can use something called the stitch command, and you can take all of those 9 observations and put it into one, combine it, covering the full spectrum, or the full range. So when you go into class and you want to look at the emission lines and analyze them, you can basically zoom in on your desired emission line, then you can basically tell the program, I don't want you to worry about anything except that emission line. So you have to tell it to ignore the left and ignore the right. Oops. And then you tell it, I want to fit a Gaussian. And you can fit from 1 peak to a 5 peak Gaussian. And then you basically click to the left and the right of the peak that you want to fit to. And then you get a nice little curve that shows where your Gaussian is, and you get some information like the peak of each of them, where it's centered at, and the area underneath that. And then you can go to the Cologne database for molecular spectroscopy, or NJPL molecular spectroscopy database, and you can compare the rest frequency to the frequencies that they have in those databases, and you can tell what molecules you have. So here's a picture of the full spectrum. And you can kind of tell there's definitely some emission lines, like right here, right here. Let's see. And then I zoomed in on the CO emission line, which was the brightest one. So it's clearly got this double peak picture, which is actually very telling of what's going on. So in the circumstellar disk, it's rotating around the star. So because of its inclination, you can kind of see a little blue shifted part and a little red shift part. So it tells you that it's rotating at like a Keplerian rotation. So I actually fit a 2-peak Gaussian. Here it is. And I also looked at an HCO plus emission line, same kind of double peak feature, and the same with the CN emission line. So in a paper that was recently submitted to APJ, they looked at the total line intensity, which is basically the area under the Gaussian times some efficiency factors, which is right here. And in that paper, they fit using a Keplerian rotating model. I just wanted to see what happens if I fit just a pure Gaussian. So you can clearly see that the just pure Gaussian method underestimates all of the values. So what you can actually do is take the ratio of those two and see and get a correction factor. So if you just want to do a Gaussian method, you can correct it for this. So what else did I do? I also looked at trying to estimate the temperature, which is not as easy as it sounds. So once you get the Gaussian fit and everything, you have to assume that the gas is optically thick and the gas is thermalized. So basically, that optically thick means that the line brightness temperature, so your signal, is about proportional to the excitation temperature, and that thermalized means that excitation temperature is the kinetic temperature as well, which for 12CO is a good assumption. So models predict about 4 to 20 Kelvin, and if you go to the Zuckerman and Palmer 1974 paper, you can get this your signal to temperature estimation equation with this dilution factor, which is just the solid angle of the main beam and the solid angle of the source, which in the paper that I used assumed about 2.8. So I estimated about 2.63 Kelvin, which is not very close. But this actually can tell you something really important. The CO in the disk may actually be structured or like clumpy. And this equation kind of assumes a smooth distribution and it's all the same. So there may be clumps over here that are cooler and clumps over here that are hotter. So in addition to the structure, temperatures can also tell you what temperatures you need to form planets. And then it can also tell you, you can look at the theoretical temperatures from like the lab or models, and then compare it to what you actually estimate. And maybe there are some other mechanisms that cool and heat the gas that we haven't taken into account yet. So there's definitely a lot of work that could be done there. So for future work that I could possibly do, for this specifically, like Calcium 15, I would want to zoom in on each part of the spectrum and see what emission lines are there that I can detect above the noise floor. Then take all those and try and estimate the gas temperatures for each one. Maybe taking into account the clumpiness. Determine some column densities, and then there's actually some hyperfine structure found in CN and C2H, and hyperfine is just like higher orders in rotation, so electron spins and such. But in general, I also want to find other stars in that point of the evolution, so you can confirm, deny, or maybe edit the theory on star formation. So I just want to thank Christina and Dr. Gassner for helping me with everything, and are there any questions?
Can you go back to one of your plots? I don't remember what side it was. It was one of your initial. Maybe go back. Go higher numbers.
Higher numbers?
Yeah.
Okay.
Okay, stop. Oh man, now I forgot what my question was. Never mind. I'll come back to it. Maybe it'll come back to me.
Okay, so I actually want the same plot, so maybe
Okay.
my question will come back to you
Maybe.
first. So the temperature that you have there, is there a difference between the T peaks that you have?
Yeah.
So one, is it in Kelvin?
It's basically antenna temperature, which you can kind of interpret as signal. It's in radio astronomy, you can do that. It's not actually the temperature of the gas, it's the temperature of the antenna.
So temperature of the, I'm sorry, I don't know radio astronomy, but so it's the temperature of the actual
The detector.
antenna.
The detector.
Or the detector.
Yeah.
Okay. Right. Right.
That's temperature measured in what, in kelvins?
I believe so.
So what does such extremely low temperature mean?
It's just the
So it's not the actual temperature of the detector, right? 0.3 Kelvin.
normalized to you can tell like when you have no detection and when you do have detection. Those normalized.
Those are really temperature.
It's a testament to the powerful lectures that I give that every one of you have had the definition of antenna temperature in this course, but it's not clear what it is.
I remember my question. Can you go back to the side with the full spectrum?
The full spectrum. Okay.
Is that the polynomial subtracted spectrum? So you get like a
Yes.
polynomial fit, and this is like subtracting that. That's what you get after.
I believe so. Yeah.
That's really strange.
Can you go to the previous slide again?
This one?
Looks like there's significant overgaps and wings on both sides. Is that just noise?
Part of it is when you have to tell it to ignore some parts of it. Like I said, the left and right part. So I could probably change it and ignore over here instead of over here, and that may change it. But it said that was the best fit for what I had chosen.
So what is the physical meaning of those non-Gaussianity? What in the English is causing it?
In the image causing which? Sorry.
This non-Gaussianity on the both sides of the Gaussian.
Probably noise.
It's noise or a Nobel Prize. Right? So it'd be interesting to figure out what the difference is.
Wish it were either.
It's probably not meaningful, but it's not noise. Yeah.
It's fast rotating gas, actually.
So it is interesting. It's just not quite a Nobel Prize.
No, exactly.
Yeah. So it is physical then. There's some physically interesting stuff in there. Any other questions? I have some questions. Go ahead.
So can you tell us anything about the point information judging from this data?
I would have to do a lot more estimation of temperatures and column densities. And you have to do all the like stages of evolution too. But the recent almond image of that lovely disc with the gaps in it that was published recently, we're on our way.
Okay, I have a few questions. Maybe you don't know the answers to some of these, and that's just fine. Just say you don't know. That's a lot easier. So how representative is this source?
Is this source?
Yeah.
Um,
Is it, if you understand this source, does that mean that you understand all sources like it, or?
No, that's another thing that I would like to do in future work is get multiple samples of each, but that's very
To
difficult.
see the variation?
Right.
Okay. On 5, what are the wavelengths of the pictures, if you happen to know?
On slide 5.
Yeah, it's those nice pictures.
Oh, I do not happen to know.
Okay,
I
on
can
8,
do that.
what's the variation that's caused by the user? It sounded like this is an interactive process where the user
Right.
maybe clicks on certain.
Right.
And if you click on the screen 10 different times to calculate the same thing, do you get the same answer 10 times?
You don't get the same answer, but it's very similar. I would have to go in and actually do it probably like 100 times and figure out.
So one way to do this is to write a script that does it automatically.
Right.
That it's not just dependent on the.
So it's like done iteratively, the fitting?
The fitting, I do it myself manually in this program, but writing another program to do it multiple times would be good.
On 9, what is there's a feature at 240 gigahertz, I think. You see it goes
Yeah.
negative to negative antenna temperature.
Right.
So one question is, what is that?
I'm not actually sure.
Is that an absorption line?
Could be, no?
Yeah. My guess is it's either noise or a Nobel Prize.
There's a couple too.
Probably neither, again.
You probably need to.
Right.
It's correct.
There's one here too. I'm not
yeah.
really sure
Yeah.
if that's noise or.
Do you happen to know, Joel?
I think it's just a bad detector channel.
Okay, because it could be an absorption line, but.
Yeah, I don't think so.
So I was going to ask the question about the units of the temperature. It just seems like offset subtraction and normalization probably happen because you have 0.
Right.
And that's not 0 Kelvin.
Right.
You could convert this into something that is actually an absolute antenna temperature if you wanted to. You could even convert it to Jansky's, I bet.
Right.
Or whatever the units at some point. Do you know how to do that?
I would have to look into more of the class program is very difficult and there's almost no documentation, but.
Okay,
I
but
can
you
figure it out.
haven't done it yet?
Right.
Okay. Go to 15. Are these equations, I'm not familiar with these equations, are these equations right?
According to the Zuckerman.
Did you derive them?
I did not myself
Okay.
because I'm not
Okay.
as knowledgeable, but they seem to make sense to me.
Okay, and that temperature there, the
That's
TCO,
yeah.
you calculated that from these equations,
Right.
right? And I think that's meant to be the actual temperature in space of the gas, right?
Right.
Okay, and I know you described this a little bit, but I just want to ask you again, is that correct?
Is
Is that the temperature? Yeah, is that
Oh,
the
no, I don't
temperature of
think
the
so.
CO?
I don't think so. I think it's clumpy and there's probably, parts where it's not, it's
So,
more.
so maybe the treatment with these equations isn't quite reflective of the physical
Right.
situation. Maybe these factors have to be changed a little bit or something
Right.
to properly reflect what.
Yeah, I
this
think
is really about.
there would definitely be some like the dilution factor kind of.
That's the clumpiness.
Yeah, to affect that.
Yep.
So when you say the models predict the 4 to 20K, so do they include all of what you said? Because I mean, that's obviously higher.
The
than temperature that you have.
Keplerian rotation, I believe, is in there, but I'm not sure about the companies. If it takes into that into account.
Any other questions? Joel, you must have some.
I have some vague answers, but.
Oh.
Yeah, I mean, these models are for a viscous accretion disk that's illuminated by a star. So these are the temperatures that you predict. I think Katie's explanation is probably right, but we won't know until we have an image.
Right.
So maybe Alma, maybe another interferometer can give us an image of the CO at the resolution you need to see if that's.
Do the HL tau observations from ALMA give any suggestions at the appropriate values of these numbers, at least for that system, that you could translate to others?
Well, the things like the forward efficiency and the beam efficiency, these are given to us by the instrument team, and, you know, we worship them and we think they're right. Things like the dilution factor that assumes a source size and a sort of typical smooth beam for the telescope and things like that, they can wiggle around, especially the source size. And that's probably where the dilution factor is going, and that's probably what's wrong.
Okay, I guess that's it. Did you ever think of your question?
Yeah, I asked it.
Oh, okay, that's right. Okay, I guess that's it.